This is lecture 18, so we finally made it, and this is super important stuff. It's what makes embedded systems work, and it's what makes embedded systems really cool. So essentially this is part of real-time programming, and you've probably heard that term many times before, but now associated with interrupts, and it's going to make more sense. Okay, so my approach to this is kind of, first I'm going to show you everything kind of at a high level, and then slowly work into the low level details. And so these are interrupts, so it is something new, but it's just very similar to what we already know, which is subroutines. So subroutines is a piece of code that's called, or program flow control is transferred to under program control. Essentially, an interrupt is essentially a special subroutine that is called not by program control, not by instructions, but by external hardware. So an interrupt gives an external hardware the ability to execute a piece of code, and as you'll see, that code that it executes at a higher priority than the other code. So a massively important topic in embedded systems. This can be super complicated. And the issue is that we don't go there. This is the introduction. What we're going to do is it's weird at first, but it's not that complicated essentially because we only have one interrupt. Maybe even a low-end system, low-end off-the-shelf microcontroller has 10 interrupts, and if you use all 10 interrupts, you'll have a very interesting system. So we're getting ready towards experiment 7. We're not going to introduce that today. That will be the next lecture. So it's nothing really beyond that. What you're going to be doing is implementing the stuff that I tell you about in this lecture. So next lecture, that includes experiment 7, you'll get a repeat of this information. So this is the RISC-V microcontroller. What's interesting about this, and you've seen this before, is pretty much everything, all this stuff, all that stuff has to do with I/O. The reset and the clock don't really have anything to do with I/O. Now the issue is this is a microcontroller, which means it's controlling things, which means it's controlling things by reading stuff in and sending out control signals. So it's generally speaking, it reads the status of something and sends out a control signal. That's what makes the world work here. The computer you're interacting with the computer, you do so via I/O. So the context here, like I said, computers interact with the outside world, and so they have various ways to do it, and we've seen a couple ways. So we've done I/O on this thing, and the two main ways we'll say programmed I/O are port mapped and memory mapped, and the RISC-V uses memory mapped I/O. Port mapped I/O essentially will have dedicated instructions for I/O. We don't have that. Our RISC-V uses memory mapped, which means it reuses the load and store instructions for I/O. So there's also something called direct memory access. The issue is this is kind of external controlled, we'll say. And then we here have the other form that we're going to talk about today, interrupt driven I/O. And once again, you can argue it's externally controlled, but I like to think it's externally initiated. So a little bit of a gray area there. So computers in general, I mean, what do? They sit there and wait for you to do something. And so the issue is that there's two ways to wait for you. So is this computer always going to say, hey, do you got something for me? Hey, do you got something for me? Or the other way is to say, hey, computer, I got something for you. So if the computer is constantly asking you for something, that means it's using instructions to do something. It's using instructions to do something. That's great if there's something needs doing. But most of the time, particularly with human input, most of the time in computer timing, you don't have anything to do. So you don't want to waste instructions asking the external person or whatever, the human, hey, do you got something for me? Okay, so what we're going to do here is use interrupts to get around that thing, and to keep in mind that typical goals of any embedded system is to be responsive. So if you press a button and see a delay, you automatically think, hey, there's something wrong with this thing. I'm not going to buy this thing. Also, when you're designing a computer system, the idea is to keep the amount of hardware appropriate for the job. So you can overkill it with the world's fastest processor to blink an LED, but probably not a good idea. Your boss probably doesn't want you to do that. And lastly here, anything you're designing, generally speaking, you want to keep the throughput high. Now the throughput is the amount of useful work any computer does. So this is a little bit tricky when it comes to embedded systems, and you'll see in a second here, but we still like to think throughput. Keep the throughput high, which means don't allow the computer to waste time. Okay, so once again, hard to make generalizations. We want to keep the throughput high, but the goal for our embedded system is not to always be doing something super efficiently, because quite frankly, sometimes in any computer system, there's going to be times when there's nothing to do. Okay, so if there's nothing to do, you can do stupid stuff. The problem is you don't want to do stupid stuff when there's something more important to do. Okay, and that thing, stupid stuff in this context means something that's going to lower your throughput. So if you got something important task to do, you go do it. You don't do stupid stuff. If you do stupid stuff when there's important stuff to do, it's going to lower your throughput. So anyway, there are a couple possibilities here to increase your throughput. One of them, of course, is to offload some of your responsibilities to a separate piece of hardware, like a memory management unit or a graphics processing unit, blah blah blah. So we certainly have that ability on FPGA, where if we need something done externally, like maybe multiplex displays, we just model it and include it in our project. And so anyway, there's a couple options for you. And okay, so once again, our goals here of any processor to keep the size appropriate is we try to keep our processor busy, but not so busy that it can't do what we're asking it to do in a timely manner. And so the idea here is we are going to have the processor do stuff under programming control, like execute instructions, and also we're going to give the external devices some ability to have some say over what instructions the program's implementing. So essentially, we're going to have some external device initiate the ability for the microcontroller to go do something. So it's going to be program flow. Some external device is going to say, hey, I need this done. It's going to make, we're going to set it up such that some external device can go make the processor do something that it wants it to do. Okay, so let's do this. Look at this. So yeah, we essentially what we're trying to do is, embedded systems in general, it's a huge issue. We're just going in one area, and then we're going to try to keep the I/O computationally efficient. Now there's two ways to do I/O. There's under program control, which is a polling. Now you got to come away with this word. Polling means I'm constantly asking, like, hey, do you have some input for me? Hey, do you have some input for me? And that's going to be very inefficient, because most of the time the processor is not going to have, or the external world isn't going to have some input ready. Yet we're wasting instructions, asking that external device whether it has input. So what we're going to do instead is have that external device tell the processor, tell the microcontroller that, hey, I need some work done, and we're going to once again do that through interrupts, and that's our interrupt I/O. So this is a classic polling loop here. What it's doing is it's inputting a value It's inputting something from the outside world. It's masking the first bit. If that bit is not set, then it goes and does a loop here. So what we have is a polling loop here, and until someone presses a button, the code is stuck here. So that's not necessarily bad. It's only bad when we have something else we need to do. So if you're stuck in this loop, that means the microcontroller is executing instructions, and it's really essentially stuck there until someone presses a button. And that could be, it could be a long time. So once again, if you're stuck here, you're not doing more important things, such as, restarting the dude's heart. Okay, so it's really important not to get stuck somewhere where you don't want to be. So the issue with interrupts is there's two primary purposes that we're going to use them for. One is we're going to increase the system throughput by avoiding polling loops. So we're going to, instead of polling, we're going to have the external device generate an interrupt, and then the microcontroller is going to do the right thing. And so under that condition, generally speaking, we get more efficient, more efficient system, but more importantly is the response time goes down. Now the issue here, they call them interrupts because an external device interrupts whatever the microcontroller is doing, and the microcontroller stops what it's doing and executes another special piece of code that the external device wants it to execute. And the notion here is that this special code that the external device wants it to execute is going to run at a higher priority because it's been interrupted. So the processor's been interrupted by external hardware. Go run the special code. So that's the general outline of interrupts, and you're going to see it's really similar to subroutines. Essentially, is we're just going to have some extra hardware where we need to store the same things like a subroutine called. And so what we have here is the CSR register, which is a control, and it's not a state register, it's a status register. Got to go saying that one. Whatever. Anyway, but there's essentially, this is our new programmer's model. What we have in there is 3 registers. Okay, so there's two 32-bit registers, but there's also a 1-bit register, which is essentially a flip-flop. The module is right here. You don't have to worry about it. It's given to you. Inside this module is these 3 registers, and then you have some control stuff going on as well. So this is once again, this is our little module that's going to help us get things working here, and we have 3 registers in it. Don't need to worry about what those registers are now. And so the issue is when you call a subroutine, this is your subroutine call stuff. You call a subroutine and it puts the address of the instruction after the call. It pushes that address. It puts that address into the return address register. So it's taking that return address, putting it in a register. Okay, then it loads the program counter with the address of the subroutine, executes the subroutine. I execute a return, and the return essentially loads that return address that got saved as part of the call instruction. It loads that return address into the PC, and then I go back essentially to the instruction after the call. Okay, so an interrupt is super similar. So instead of a call, I receive an interrupt. Okay, so what I'm going to do here is I need to store a return address. It's essentially the address of the instruction after the instruction I was executing when I got the interrupt. Okay, so that's going to be the return value, and what I'm going to do here is store it in one of these registers. So that means when I'm returning from the interrupt, I am going to take what's in that register and put it back into the program counter. So the second thing I need to do is load the address of we'll call it that special subroutine forevermore. We'll call it the ISR, which is the interrupt service routine. we need to load that address into the program counter, which we do. And then we essentially process the interrupt service routine, which is essentially almost exactly the same thing as a subroutine. The only difference is the return instruction. We have a special return instruction here. So the return instruction for interrupt service routine is the mReturn. It does essentially the same thing, but it takes that address we stored, the return address, we stored it in this register. It takes it out of that register or copies it from that register, puts it in the PC. So same exact mechanism, it just uses a little bit different hardware and a little bit of different instructions here. So this is a call which is done under program control. This is for an interrupt which is kind of done under external control. So here's our program here. We're going to write an interrupt driven program that essentially all it's going to do is toggle an LED every time I get an interrupt. Okay, so and there's a couple things involved in this. So essentially what we have here is the interrupt input. So this some external device here is going to be generating an interrupt, and remember, this is an input to the microcontroller. Okay, and essentially what's going to happen is the controlling state machine is going to see that an interrupt got generated, and it's going to go into that special sequence of stuff we saw here before. But what we want to do in this for this program is show you just a real skeleton version of an interrupt driven program. Essentially it actually does work. It does blink a light. So this is our a couple things here. This is our new module here, and you can see that these two values here are essentially potential program counter values, and they are going to have the ability to be loaded into the program counter, which means we have to expand the size of this mux here. What else do we have here is we have this, we didn't really say anything about this, but we have this this is the external interrupt. We have it fed through a AND gate, and what we have here is the ability to allow that interrupt to go into the state machine or not by turning this bit on or off. Remember, this is a register, essentially a flip-flop, which is 1 bit. So if this register is a 0, that kills this gate here, and the state machine will never see any interrupt coming in on this signal. And so what else is interesting about this? A couple other hardware changes here. We'll actually go through those a little bit later. We'll go through those on Monday. So that's the general outline. Most of everything's still the same, a couple of different modules here. Okay, and so what we have here, interrupt driven program, generally they have 3 parts. At least I think they do. They have some initialization code both for the program and essentially you got to get the interrupts working. You got to do some stuff to get the interrupts working, as well as you've used this before in subroutines, kind of the init code subroutines. It's no different for an interrupt driven program. Put some init code in there. Second thing here is we have some main code and then the ISR code. So the main code is essentially also the main task, or most importantly the background task. So the background task and the foreground task, now these are important words. The ISR, which is that special subroutine that the hardware is going to call, is now called the foreground task. So the background task typically is running until I get an interrupt, and then it transfers control to the background task, which is interrupt service routine, which is just a special subroutine. It's just a special piece of code somewhere. But it's important to use the terms main code and ISR code and background and foreground task. So this is our new state machine. Now we modified it to have an interrupt state here. Okay, the interrupt state does some special stuff that essentially we're not going to get that deeply into now, but essentially makes the interrupt architecture happen. Okay, so we like using that term architecture anywhere we can. We are describing the interrupt architecture now. So what we have here is essentially this code here, or the state machine, is looking for those interrupt signals. Okay, so if I'm in an execute cycle and the instruction is not a load and the interrupt is asserted, then I go into the interrupt cycle. Okay, so if it is a load type instruction, I transfer to the write back cycle. It doesn't matter if there's an interrupt or not. Okay, in the write back cycle, if there's an interrupt, I go to the interrupt cycle. If this pen's freaking out. Otherwise, in the write back, if there's no interrupt, I just go to normal processing. So what you want to take away from this diagram is the fact that before it acts on an interrupt, meaning before it goes into the interrupt cycle, it always completes the instruction it is currently executing. So the ramifications of that are your external device is not synchronized with your microcontroller, meaning that the interrupt can come in anytime. It can come in right in the middle of an instruction. No big deal, but the issue is whatever instruction's executing, it completes before it goes into an interrupt cycle. So super important. Okay, we're getting there. I have the ability to mask interrupts. Essentially, the masked interrupts is I do that by writing that register, and that register essentially, I'll just redraw it here. It has the ability to turn this AND gate on and off. So if this value is a 0, that value is a 0. If this value is a 1, this value becomes whatever this value is. So it allows the interrupt signal to pass through this gate. And you can see, if you see, I don't want to flip back to it, that this is the microcontroller and this is the interrupt input on the microcontroller. So we have the ability to set this register. Essentially, we can write it via instructions, and we'll see that a little bit later. And I guess we'll see it now. So this is the program. This is an interrupt-driven program that essentially blinks a light. And so I wanted to step through this. It looks completely gnarly, but if you step through it a piece at a time, it's super doable. Okay, so the very first thing I need to do here is I get the LEDs here. So I need to get it in a port address. So that's just a really comfortable thing to do. Now X15 here has the LEDs address in it, and I can use that for my store instructions that you'll see later. So the next thing I need to do, and this is part of the initialization of the interrupt, is I have to write the address of the interrupt service routine. Okay, so here's my interrupt service routine right here. I have it with a fancy name, ISR, and what I'm going to do is load the address, essentially it's the address of this instruction, into X6. Okay, and then I'm going to store X6 in this value right here. So you see, we've got a new instruction there. So this new instruction essentially is going to take, and it's a real instruction, it's not a pseudo instruction, it's going to take the value in X6 and write it into this register. Now you can look this up in the manual. We'll go over it a little bit more clearly next time in the next lecture. We'll actually go through this program again because it's so important. So I got two registers here. These are two registers that I'm using one as a flag, and you'll see that come up, and then I'm using one to store my output value. Remember, I'm blinking a light on this thing, and I want to keep track of whether the light is on or off. Okay, at this very next instruction here, I am going to turn the LED off. So I'm starting from an off state. So more initialization code there. So we got more initialization code. Generally, the last thing I do when I'm initializing something before I go into the main task or the background code, so this is the main code right here, or the background code, is I have to enable the interrupts. So I load a register with a 1, and then I take that value and I write it into the CSRMIE register. So this goes into CSRMIE, and that's what that does. Yeah, I thought that was an array, so well. Okay, so that turns the interrupts on, so I'm ready to get an interrupt. Now here I am in the main code here. So this is okay, back again. Hopefully got the pen fixed. So this right here is pretty much our main loop, and I know you're going to probably look at it and think, hey, it looks like a polling loop. Yeah, it's a polling loop, I know, but I can't think of a better way to present this example. So what it's doing is it's comparing x8 to 0. Now, what we did was we initially put x8 as 0, but so I mean it's stuck in this loop here. It's jumping back to itself so long as x8 is 0. So how does x8 get to be anything other than a 0 if it's stuck in this loop? Well, the issue is it gets an interrupt. Some external device generates an interrupt. Under that condition, it branches the vector address, which is the interrupt service routine. And inside the interrupt service routine, that's when I put a 1 or some non-zero value into x8. Okay, so that being the case, I got the ISR turns that x8 on, which I'm using as a flag. I call it a flag. It doesn't really do anything. It just tells me that something happened, like an event happened. And so the issue here is x8 is suddenly not 0. It breaks out of this loop and falls down to the next instruction. Okay, so in this instruction here, what I'm doing is I'm toggling 1 bit in the x20 register, which is I'm using as kind of the LED output storage register. And then I am writing it. So I'm toggling that bit and I'm writing a new bit to the output. When I write that new bit to the output, it essentially takes the state that the LED is in and it changes state. So if LED is off, it turns it on. If the LED is on, it turns it off. This is what these two instructions here do. Okay, so at that time, that's kind of the bulk of my algorithm, but I need to do some administration work on this thing. And so what I'm going to do is turn the flag off. Remember, the flag is what allowed me to break out of this loop. And then, most importantly, I'm going to re-enable the interrupts. So this line right here, you can see it's exactly the same as this line, meaning that I mean, we didn't turn the interrupts off, right? No. What happens is, as part of the interrupt architecture, the interrupts are disabled automatically. And so we'll get more into that later. So once again, once I got the interrupts re-enabled, I jump back to this loop here. And it's going to be stuck in this loop until I get another interrupt. So that's basically the operation of this. Like I said, I will go over it again in the next lecture just because it's so vitally important. And so there's a couple more things here. So essentially this is just a summary of what happens here. So what happens is some external device connected to the interrupt pin on the microcontroller generates an interrupt. We're going to assume the interrupts are unmasked. An unmasked interrupt means an enabled interrupt. That means the device goes into an interrupt architecture, but the first thing it does is, number 1 here, should be 1, it completes the instruction, the execution of the current instruction. Remember, these takes a couple clock cycles for these instructions to execute. Additionally, the interrupts are asynchronous. They can come in any time, and so the state machine is set up such that I finish the execution of the instruction I'm on. Okay, at that point, I go in the interrupt cycle. Part of the interrupt cycle has a couple different, well, it has 3 different responsibilities. One is it disables or it masks the interrupts automatically. Additionally, it saves the address of the instruction after the instruction that would have been implemented, would have been executed had I not got an interrupt. It saves that address into the CSR registers, one of the registers there. And so what's going to happen is well, you'll see when we return from that. And so the other thing it's going to do is it takes the address of the interrupt service string routine, which we previously stored somewhere in one of these CSR registers. It's going to take that and load it into the PC. Once I load it into the PC, I will start executing the instructions in the interrupt service routine. So so you're executing your ISR and you finish, and the thing you do here is you execute a M return or MRET instruction. I think it stands for machine return. Essentially what it's going to do is going to take that PC that you stored, PC value that you stored in this register here, it's going to take it and put it back into the PC. And remember, this is the address of the instruction after the instruction you're executing when you got the interrupt. So that's essentially your processing got interrupted. You're going to go back to the next instruction, and I'm going to say that's it. And it's not RISC, it's not rad, it's RISC. Gotta go change that one too. Anyway, that's it for the summary there, and I think we're going to call this one done. Super important information. Once again, I will go over this information again with the next lecture in a little bit different amount of detail.